Hi, welcome to the second lecture. We are going to talk about the limit of a function. In this video we are going to talk about limits in general. It's item number 1. We are going to talk about limits. Then we are going to talk about one-sided limits. Then we are going to talk about infinite limits. Next, we are going to talk about vertical asymptotes. Next item would be something called the squeeze theorem. And the last item for today would be limit laws. Okay, so I have item A, B, and C, D, E, and F. Okay, first one, we're going to talk about limits. We already saw in the previous lecture that limits come up in the context of calculating either slopes of tangent line Another important application of limits came up when we talked about figuring out the instantaneous velocity. In examples done in the book or in class, we saw measuring things such as volumetric rate, how fast does a certain tank get emptied or filled up, and such issues. They all come back to the concept of limits. Let's go ahead and try to understand the following notation. All of these problems have something in common. They start with some function that is given at the outset. So if we have something given to us by some formula, and I'll just write it as f of x. All of these problems have the following in common. They ask you to calculate the limit of that function as the variable in it, x, approaches a certain quantity. Let's call it a. And they ask you to find out what that limit is. That limit gets to be written typically as just L. Question we have is, well, what does this mean? One simplified way of describing this is to say that as x comes very close to the number a, this x as it comes close to the number a, y gets very close to the number you specify here, L. This is probably first time you see this notation and might look a little bit odd to you. So we go ahead, pick up a simple example similar to the ones we have seen, do that problem, and back to this notation later on. We try to digest that notation. We have to look at it, write it often, talk about it often until notation becomes second nature for us. Everything in calculus is going to depend on that. Let's take a very simple function here, f of x. So here's going to be an example. F of x is equal to x squared minus 9 over, say, x minus 3. So we are comparing this example here. My function is given by this formula. Now I let a, can you guess what is the point of interest here? A, of course, is going to be 3. A is given to be 3. Question is, find L. That is, find limit of. So here's our expression: x squared minus 9 over x minus 3 as x approaches 3. Now we are going to have an experimental way of answering this question. So here's an experimental answer. Or I should say experimental solution. Experimental means that we are going to avoid doing too much algebra. We are going to try to go to very basic concepts, things that are going to be intuitive to most of us. Even if 3 years after this course you're not dealing with the formulas all that much, you still be able to go through the same steps and figure out the answers for yourself, even if you don't find a formula book around yourself. The way to answer this, the concept that we have to follow is explained here. We let x, we want to follow, see what happens as x goes close to 3, what happens to y. Remember, y is just this expression. This is our y. As x come close to 3, what happens to y? Remember, in a variety of these problems, in the more interesting ones, you cannot go ahead and just say, let's take x to be exactly 3. If you let x to be 3 here, you get 0 in the denominator. That's a one red flag. And you get also 0 in the numerator. 0 in the numerator and 0 in the denominator becomes actually a bigger issue than just having a 0 in the denominator. So to answer this, we go ahead and make a table for ourselves, either vertical or horizontal table, whatever suits you. I go ahead and try to make a table. I make room for myself. Here's x, here is y. Our destination is 3 here. At 3, y itself is not defined in this example. This is not it's undefined. But there's no problem taking other values for x. For example, I could start at 2, plug the 2 here. 2 squared minus 9, it's 4 minus 9 is 5, over minus 5 over minus 1, and I get the answer equals, turns out to be 5. Now let's let x come close to 3. How do we come close? In a standard way of coming close, just to use a string of 0.9s, but I come to 2.9. Take 2.9, plug it here, use my calculator, or just do it by hand, and you calculate, the answer turns out to be 5.9. Now we still want to come close to 3. Take number 2.99. I plug it in this and simplify, and you get 5.99. Now in this fashion we are coming close to 3 from the left hand side of it. I could come from the right also. So for example, I could have started at 4. If I plug 4 in this expression, 16 minus 9, that is 7 divided by 1, this answer turns out to be 7. If I have, well, now I want to come close to this. From 4, starting at 4, I want to come close to 3. Here's a standard way of coming close to 3. Next number is going to be 3.1 coming close. If I take 3.1 and plug it here and solve this, I am going to get 6.1 as the answer. If I want to come even closer, it's going to be 3.01. Could have used a variety of other numbers here as well, but these are rather standard ways of coming close to some destination. I plug it here and I get 60.1. So now we look at our outputs, try to discern any pattern as to we see here. What is happening to our y's? as you see the y's here, all of them are approaching to 6 from here. 5, 5.9, 5.99, and so on, they are all approaching 6. This one also approaching towards 6. So here we can say our answer as x approaches 3. So we say as x, this arrow you are going to read it as approaches or tends to or comes close to, or any of these type of expression. As x approaches 3, y approaches 6. So that is an experimental way of finding a limit. In this problem, perhaps you remember things from high school you could do so that you get the answer quickly, but in a more complicated problems, I advise you to start with the experimental approach to get a sense of what's going on, and then you can go ahead and try to do it with the algebraic approach. Different kind of a test might ask you a question from different points of view. So this is, if I ask for an experimental style of solution, you make a table. This is going to be the center of your table. You try to approach it, and then you try to guess the answer for that. So here we got our answer. Answer turned out to be 6. Now, in next item, item B was one-sided limits. One-sided limit. In some problems, we might be restricted to approach our destination from one side only. Either is a natural restriction or an artificial restriction, whatever it is, we might be limited to just half of this picture. Like you might be allowed to go close to 3 from the numbers below it, or you might be allowed to go to 3 from the numbers above it. When you are doing the following, these numbers, if that is what you want to pick and that's what you want to work with, you refer to this as x coming close to 3 from below. To indicate below, you put a negative sign on top of the number that you are getting close to. So this kind of means 3 minus tad bit. You are staying to the left. These numbers are all obtained as 3 minus something. On the other hand, if you want to work with this set of numbers, if this is what you care for, you want to talk about them, the notation for this is x going to 3 plus. Okay, 3 plus means our numbers are a little bit larger than 3. These are the type of numbers we have. This means the numbers are a little bit less than 3. Notice that we always write with the arrows pointing to the right. That's a standard notation, even though in a table our numbers are marching in this sense. So just observe the notation as you work it. So one-sided limits the notation for it might be like limit of f of x as x approaches a from below or from the left, and the other one is a limit of the function f of x as x approaches a from the right or from positive side. Now, just make sure you understood what this notation means. We are going to go draw some pictures and ask you some questions about these limits. The purpose of the picture is that we just don't want to spend so much time making these tables and talk about them. We want to bypass the arithmetic and just concentrate on the symbol and its notation. So I just draw some pictures here, and I'll be asking you to help me find out various kind of limits. Here is, I draw some coordinate system. And I draw a function similar to some functions you might see in your college algebra classes and such. Here's an example. Okay, here's a peculiar looking function. I call it y is equal to f of x. And just to be specific, we give some numbers. Suppose this is a point, say 3, and this is 1, say. This is 2, just so that our numbers do not collide with each other. Let me call this 4. Now the question, what is the limit of this function as x approaches 3 from left? Well, what does this mean? This means pick a creature or an object that is traveling on the graph of this function. However, restrict his traveling such that his x-axis comes close to the 3 and stays below it. So I can walk on this thing. Here I am walking on this. My x-axis, how do I find my x-axis? Well, I come down here. This is my x. My x-axis is supposed to come close to 3 and stay below 3. So here I travel. I'm still getting closer to 3. My x is getting close to 3. Question is, what is my y getting close to? Where is my y? Here is the y. Where did it come right now? Now it's here. Now my y is here. Now y is here. Well, as I come close to this point, my x comes close to 3. What happens to these y's? X came close to 3. Y gets close to, well, what's your guess? Of course, the answer is going to be 4. Now, let's try this thing one more time. Suppose I ask you, what is the limit of f of x as x gets close to 3 from the right hand side? So right hand side plus means pick this branch. This is the branch you pick. You're going to travel on this. How do you travel? Well, the restriction is that you are supposed to travel such that your x comes close to 3. So remember, this is, again, this is your x. Your x is supposed to come here. So you get closer, your x is getting closer, and so on. What is the question? The question is, what is happening to the y value? Choose a different color for the y. Here is our y value. This is my y. Here, for next value of y, I came here. Here is the next value of y. Here is the next value. Here is the next value. We are traveling in this direction. This is kind of our final destination. Our x's come close to 3. What happens to all these y's now? What is your guess? They are all approaching this value 1. So here y is equal to 1. Now, out of curiosity, if I had asked you what is f of 3 itself, the notation in this, if you remember before we crowded this picture with lots of lines, these empty circles by notation means they are not part of the picture. A filled in circle indicates something that is part of the picture. So at 3 I go up and see where I hit the graph. I hit the graph right here, and that value is just 2. So value of the function at 3 itself is just 2. So let's go ahead and draw this picture one more time. Here was x-axis, here was the y-axis, and I had a picture more or less like this. Here was 4. Here was 2. Here was 1. Here was 3. So we are asking, coming from the left, this is our final destination. Coming from the right toward x equal to 3, here final destination is just 1. If you want at 3 itself, if the function happens to be defined, there's a filled-in circle, or the part of the picture is there, well, in this case it is, and the answer turns out to be 2. So these type of questions are very simple to answer, so long as you know what is it that you are being asked to do. There is no algebra to do, there is no activity. If you know how to do it, it just takes 1 second to answer any of them. If not, there isn't any kind of a algebra activity you can do to bring you to the answer. Item C for today is so-called infinite limits. Let me ask you the following question. Suppose I have y is equal to f of x, just the name of my function, and that happens to be, let's say, 1 over x minus 2. I ask you the question, find limit of f of x as x comes close to 2 from, say, right hand side. What is this? Well, we learned our lesson, and for time being we are doing everything in experimental style. Experimental style just means that we make a table and crank up the calculator and see what kind of a pattern do we see in our numbers. So here's my x's, here are my y's. I want to come close to 2. X, I want to approach 2. I want to see what happens to the y. So let's just pick some numbers. Suppose I pick 3. Well, if I put a 3 here, 3 minus 2 is 1, so I get just 1. Let's come closer. Say I said come close to 2.1. Let's put 2.1 in this. 2.1 minus 2 is 0.1. 1 divided by 0.1, I get 10. What if I come closer? 2.01. 2.01, you plug it here, you get 100. Now, again, we are using a standard style of coming close. There are many different ways of coming close to a number. This is just one set of easy to handle numbers. So here's another one, 2001. If I plug it here, go through the division, I get 1000. So all of these numbers that I have up here, they indicate these numbers are behaving as x that is coming close to 2 from above. Question, what is happening to my y's? Where are they going to? I'm going to 1, 10, 100, 1000. Every time, every step I take, this goes up by a factor of 10. So where are they headed? Well, they are not headed toward any fixed number. So because whatever number you come up with, in the next step I'll be multiplying it by 10. So a symbolic way of representing this is to say this is infinity. Since these are all positive numbers, this is going to be positive infinity. So So the reason for infinite limits, this title means sometimes the numbers you are calculating they are tending toward infinity, and that is what we are going to write here. So we just write the answer is plus infinity. Notice plus infinity is not a number, it's not like a 2 or 3 or something, it's really a symbol. That symbol simply says that these set of numbers are going to increase without bounds, without ever stopping. What if I had come from the other side? What if I had asked you the question of finding limit of f of x as x come close to 2 from below? You again make a table just like this one. I might as well push my number to the right, so I write my answer here. Here's my x and y. Choose my numbers. Okay, what's a good number to start with? I'll say 1, and then I'm going to take another step, 1.9, 1.99, 1.999, and so on. What happens to my y's? I'll just plug it in, see what happens. 1, you plug it here, you get -1. 1.9, you plug it here, you get -0.1. Reciprocal of that is -10. You try it, -100. You try this one, -1000. So where are they going? The best notation we can use here is to say that they are going toward -infinity. So here's our notation. If x is approaching 2 from below, we are going to go down to -infinity. So that's the story of infinite limits. Story of infinite limits ties into the story of vertical asymptotes. So item D for us is vertical asymptotes. Idea of vertical asymptote is just capturing what we saw here in a picture. This is algebra and arithmetic. If you want to display all of this thing by a picture, you are going to have a vertical asymptote. Let's see what happens here. Suppose I ask you to graph y is equal to 1 over x minus 2. Okay, you need a good graph paper to do this thing, and right now I don't have that good graph paper. We just do the best we can. So here is a y-axis. Here is, say, my x-axis. Here is, say, point 2. We said in this table we can use these numbers on our picture. Every pair of numbers here represents a point. For example, this 3 and 1 means when x is 3, y is 1. So I go ahead and say at 3 I'm at 1. What else I had? At 2.1 I was at 10. That's already so high up, it will be rather hard for us to show. So let me just choose some number that is a little bit more practical. Suppose I say 2.5. If I plug 2.5 here, I'm going to get 2. If I get, for example, 2.2 and plug it here, I'm going to get 5. This is 3, 4, 5, and so on. So if I patiently put in a lot of numbers of this type, what I am going to see is going to be a curve kind of looking like this. What does this curve represent? As my number comes close to 2, y values keep increasing without bound and going to infinity. If y goes up, it means you're just shooting straight up. That is the direction you're headed. So to indicate this trend, the easiest thing you can do is to draw a straight line. The graph actually looks a lot like a straight line. It goes up like that. Since it's a function, actually doesn't cut this straight line, but that's just a technicality. This is a line with the equation x equal to 2. This one is the function itself, y is equal to 1 over x minus 2. The two of them get very close to each other, far away from origin. Any line that comes close to your graph, far away from the origin, you call it an asymptote. Here's the asymptote. If it happens to be standing straight up, you call it a vertical asymptote. There are also horizontal asymptote, oblique asymptotes, and so on. How about the other half of the picture? Other half of the picture, it was when my x's was less than 2 and I had these numbers. Let's go ahead, not to leave that out of our picture, let's have something about that. When x is 1, we remember this was minus 1. Let's go to 1.5. If I put 1.5 here, what do I get? Minus 2. What if I put say 1.8 here? I get minus 5. So that's going to be all the way down here. That's far enough for us. And the picture is going to look like, let me draw it the same style over there. These were my points. And I got a picture that looks like this. Wow, that is going straight down, and one way to show that is just to draw this line going down as well. It's the same line, same asymptote. That's what we call the vertical asymptote. Simplest way that you see vertical asymptotes is the following. You have an expression that has a numerator and denominator. You have simplified it as far as you could go. If you set the denominator equal to 0 and solve that, the solution is going to give you the location of vertical asymptote. So a simple recipe with a bunch of fine prints around it to keep the customers happy. We don't talk about the fine prints too much. It's a denominator, excuse me, my software behaves right here now or not, to get vertical asymptotes. We're going to abbreviate vertical asymptotes with VA. So to get vertical asymptotes, set denominator equal to 0 and solve. There's a lot more to say, of course. Again, this is a simplified description. The word is a lot more complicated than that. Okay, next item that we are going to take a quick look at, something that's going to be used a couple of weeks from now, is something with a funny title. It's called the squeeze theorem. So here's item E. Okay, this is something a little bit harder than being between rock and a hard place. Imagine you're between the rock and a hard place, and the two sides are closing in on you, and just you're going to be crushed in between. The theorem simply says you have nowhere to go in that situation. It's a statement that best described by a picture. You can read the statement in the text itself, but on a picture it's going to be easier to describe. Suppose I have one function. So here's some function. Let's call it y is equal to f of x. And suppose I have some other function as well. Let's say here is my other function. Let's say y is equal to g of x. And for good measure, suppose I also have a third function. For the third function, I know that this is trapped between the other two. So I have another function y is equal to, say, call it h of x, that is trapped or being squeezed between these two functions. And these functions, one of them is above the other one. That is, f is, say, larger than or equal to g. And the two functions have the same limit at the same point. So here I have, should I use some other color? Here is some point at which they get joined. So this is point, say, A. So here's a requirement of the theorem. It says f of x is staying above g, or maybe at some points it's same as g. Next one, it says the f and g have a limit at this point, and that limit is the same limit. So whatever this limit is, it's same number. So limit of f of x and g of x as x approaches a are the same. Let's call it that L. Now we are introducing a third variable. Suppose h is between f and g. So really we have not only an f, but also we have an h and a g, and it so happens that f is above h and h is above g. If it happens to be like this, where do you think h can go? As I approach a, where can it go? Since it is between these two, and those two themselves are approaching each other, this one has nowhere to go but to go to the same limit. So we say if f is squeezed between f and g, then limit of h of x as x approaches a is same limit that the other guys had, is L. So that's called the squeeze theorem. It's going to be very few cases that we are going to use this, but those cases are going to be very significant. So we are just making a statement of this. Now for the last item for the lecture today, we have the so-called limit laws. Limit laws are a sequence of statements or theorems that if you read through it after a while, you might feel a bit uneasy as to what is it that is being said. The statements are very simple to apply. The significance of it really cannot be explained right now. You need an advanced course in math to see what is it that is being said. Let me simplify the issue and say what is involved here. Suppose you have two functions. Let's consider two functions. Let's pick two simple ones. Say f of x is, say, 2x plus 1, and let's pick another one, say call it g of x, and let's assume that is x squared. Let me ask you the following. What is the limit of f of x? I'll just be asking you to guess. What is the limit of f of x as x approaches 3? When x is very close to 3, what is 2x plus 1 close to? Okay. Let me assume that you all guessed it right, that the answer is 7. How about g? What is the limit of g of x as x approaches the same value 3. I'm hoping that most of you guessed it right, that the answer is 9. For these simple problems, we don't really have to do much, and that's really the point of these limit laws. Here, the very first statement: suppose somebody is facing the following question: what is the limit of x squared plus 2x plus 1 as x approaches 3? Now we are kind of pretending that these were very hard problems that we worked for ages to solve, and here are the numbers we got out of it. Now we are facing another problem. We can come and say, look, I have already done all the work, in the sense that if you take this question and break it into two components, this as one and this one as the other one, you're just adding these two components. If you want to find the limit of sum of two items, if possible, you can just add the individual limits. Limit of the sum is sum of the limits. It is on the right hand side. I can go ahead and say, if this benefits you, go deal with x squared first and 2x plus 1 on a separate stage, figure them out, and then add them to each other later. So all that has happened is that instead of applying the limit to the whole thing, we can apply it to individual pieces and then add it later. When is it that is legitimate? This is legitimate. This is legitimate if the individual limits do exist. If there was no problem finding them, then we can go through this process. That is, I can say, look, let's save time and say x squared was done already, 2x plus 1 was done already, and the answer is 16. This kind of idea is expressed in mathematics with the following rather hard to digest notation. They call it like limit of f of x plus g of x as x approaches some number a is the same as limit of the first one and the second one calculated separately and then added to each other. Now you are going to see lots of laws like this, and I'm really afraid that when you see these things, a wrong impression is going to be left in your mind, and later on down the road you'll make certain very common mistakes. So it's a point of pedagogy here that I really don't agree with, putting these things up front in front of the students because of that complication. Let me try to dispel something and reintroduce this in another way. Hopefully those future mistakes would not happen. Here we really have two operations to do. One is this addition, one is taking this limit. We have two things to do. On this side you add first, then you take a limit. On this side you take the limit, take two limits, and then you add them later. That is, you have exchanged the two activities. You have changed their order. Now in real life, when you have to do two things, it makes all the difference which one you do first. For example, in the morning, if you put the socks first and then you wear your shoes, or you wear your shoes first and then you put on your socks, you are going to look different. In mathematics also, when you have two operations, the order you do them makes all the difference. In some special cases, it so happens that it perhaps would not make a difference. So like if you put your pants on and then your shirts later, or you put your shirts and then you put your pants on, the result, well, typically is the same. Here we are saying that these two activities can be interchanged. Whichever of them you want to do first, that's fine. Do not generalize this thing to every situation and assume that wherever you face two activities, you can do them any which way you want. Just remember from real life. At any rate, limit laws are a bunch of statements similar to this, which essentially tell you you can exchange the order. Here's another one which is quite straightforward. Subtraction, same story. If you are subtracting two functions and then taking the limit, you might as well take the limits first and then subtract later. Can you think of other things that you might think that the order of their action could be interchanged with limit? Well, in fact, just about all the basic arithmetic operations you know about have this property, with the exception of one fine point that we are going to talk about. Addition, subtraction, multiplication, exponentiation, taking roots, and so on, they all go exactly like this. The only thing to warn about is division, and that is because the action of division itself has some complications associated with it. So let me just go ahead and write all of these things. Limit of f of x times g of x. Like if I had those two functions and I wanted to multiply them first and then take a limit, if I wanted to, I can exchange this thing and take each of the limits and then multiply them later. Or if one function and the other functions were the same, or if you just had one function and you were raising it to a certain power, to some positive power, like squaring it or cubing it or raising it to the power of 10, and then you're taking the limit, you can interchange this, meaning that you can go ahead, take your limit, and then raise the whole thing to the power later on. So n is going to be some positive number, negative number. You have to watch out for what you're doing. Finally, if you have f of x divided by g of x, and then you're taking a limit, you might as well find each of the individual limits and divide later. The only thing you need to worry about is to make sure that the limit of denominator is not 0. So you have to assume that g does not approach 0 as x approaches a. So we provided that. So here let's write, there's a fine print next to this, provided that we do not divide by 0 at any stage here. That's a kind of a fine print that is next to any kind of a division you might have. So that is there all the time. Okay, you go ahead and do the exercises of this section. It's just a lot of talk really and not much activity. It's just you are laying the foundation of limits. You are not going through the kind of homework exercises you had, say, in college algebra. So go ahead and read the section, do the problems. Each of the problems shouldn't take more than a couple of minutes for you. Good luck and God bless.